Me? So what we are learning today, I hope, Jordan, can you give me a feedback you can hear?
Yes, ma'am.
Yes, ma'am, we can
Thank
hear.
you very much. Yeah. So this is a very important topic. This derivation is about n element linear array with uniform amplitude and spacing. So far, whatever we did was related to two isotropic sources, right? Now I'm talking of n isotropic sources, n number of them. And also when we replaced our isotropic sources with other antenna like a dipole, we never did it the way we did the analysis and derivation in two isotropic. We used pattern multiplication and we just got the pattern and we left it at that. That's the scope of your syllabus. So you take the element factor multiplied with array factor and we get our pattern when it is pattern multiplication. Array factor comes from isotropic sources. All right. And then when you replace the isotropic sources with the dipole, then you use pattern multiplication. Okay. Now, going further, suppose we have n element linear array of isotropic sources. N of them, n number of them. And we are talking very specifically about linear array, and all of those elements are going to be separated uniformly. Okay, so all the elements will have the same distance with each other, and they will be fed with equal amplitude. So that is the thing, and we are going to talk, that is called the uniform amplitude and uniform spacing. Okay, an element linear array, not a planar but a linear array. One moment. What I can do is, Parth, not Parth, Pratham, uh, Pratham, can
Yes,
you,
ma'am.
Pratham, I'll make you a co-host. Please take people in when they are in the waiting room. You'll be able to see them.
Yes, ma'am.
Thank you very much. All right, now going further. Now you notice here, I have n elements over here, okay, n elements. So please note down from the screen. So each of these elements are giving out, is being fed with amplitude 1, okay. So if you notice that it has amplitude 1, okay. So you can see here, this is amplitude 1. I hope you can see the cursor. And the second element is also having amplitude 1 and so on. So the first element shown at the origin is given 1. The next one, the psi. The psi was what? KD cos phi plus delta, right? So the next element is having amplitude 1 and the phase is J psi. Okay, J psi. Because what is psi? Psi is KD cos, it's written in the line below. KD cos phi plus delta. The next element is D distance away. So there will be a phase shift of KD. Okay. Then delta is the phase shift if we are giving. Now, if I am giving same phase, then delta will be 0. If I feed them at a phase shift of pi, then delta will be pi. Are you understanding? But here, delta, if I'm saying same amplitude and same phase, delta will be 0. So the derivation goes like this. The electric field is the sum of the element 1, that is the first one at the origin. Then the second one is shown as J psi. The third one is J2 psi, and so on till the nth element will be n minus 1. Okay? You are able to see?
Yes, ma'am.
Yeah. Those on meeting will be able to see. Okay. Now, after that, there is some rearrangement done. If you equate 1 minus 2, you will get E minus Ej psi equal to 1 minus E raised to Jn psi. This is a mathematical, operation being done so that we get electric field intensity E. Okay. So please, I request you to note down this derivation till here. And once you are done, then I will go to the next slide. Please type in the chat once you are done. Pratham, you can't hear me now?
No, I can't hear you.
Is it the case for everyone?
No, ma'am, we can hear.
Uh, okay. I will take care to keep the mic close to my mouth. Let me know once you are done. All right. We will move ahead. Okay, there are some people in the lab who are writing. I'll give a minute or so. The derivation is simple so far, isn't it? Yes, yeah. You could use the chairs, students. Sitting on the stool will be uncomfortable. There are 3 chairs, shift the stool and be comfortable. Okay, boys, done? Okay. So we will go to the next step. In the next step, if you go further, you will see there is some more arrangements done. That E, if you see in the left corner, top left corner, is further divided by E raised to J and psi by 2. There is a particular reason because you want a sinc function. So look at it. Okay, you will get, if you see, the last thing that you get is sine of n psi by 2 upon sine of psi by 2. Okay. Now there are n elements. There are n elements. Remember when we did for 2 isotropic, there was a 2 E naught because there were 2 of them. Now by default, there will be a n. Okay. So that is why in the end, you can see in the right hand side that En normalized has a 1 by n. Okay. Now in the numerator, you have sine n psi by 2 here. Okay. Now, if you can see, there is a sine n psi by 2 here. I'm very sorry. Yeah. In the numerator. In the denominator, we were supposed to have a sine psi by 2. Okay. But when you have very large arrays, very large, Not elements like 4 or 5 or 6, very large, 100, 200 elements. Okay, that time that sine of psi by 2 becomes approximately equal to psi by 2. The sine function is as good as the angle. Okay, but you will see when I take problems, I will not let you take sine or matlab approximate it to psi by 2. We will take it as sine of psi by 2. So please note down. With this, the derivation ends. It's a very simple derivation. Okay, please note this thing down. I think Pratham has lost the control of co-host. Jordan, can you take those in the waiting room in? I'll make you the co-host.
Okay, ma'am.
Very sorry.
Ma'am.
Let me know once you're done. Hello, Jordan. Why did you raise your hand? Is there a doubt?
Ma'am, that first step, is that a formula or something, ma'am?
The
Like how?
first, the one in the top corner,
Yes, yes.
it has come from here. Can you see at the bottom of this slide? It is
Huh.
carried on from here. It has come. We have come this far, and then on the next slide, it is brought in to work on it. Is that okay?
Oh, okay, okay. Okay, ma'am.
This derivation is very important. I've already told you guys in the past. Two key numbers. So that's how it's very good. अब तुम्हारे क्या से बचा है important key. Done? More very cross by that delta. Anyway, we'll give it the first slide. That is very cool, no? Compared to your classroom. Okay. Can I move ahead? Okay.
Yes, ma'am.
So I'm moving ahead. Okay. I hope everybody online are also okay. And okay, so what you notice here is that the electric field that we have just observed is a sinc function. Okay, this is called a sinc function because you noticed that there was in the numerator a sine function and in the denominator there was a sine function, and the one in the denominator, no, is is an angle which makes your beam sharp. So when the psi by 2 becomes very narrow, the beam becomes very sharp. Okay. So it is, you understand that this is how the function is, and this is how your radiation pattern will appear. Okay. All right. Now, if you have to do evaluation, okay, now this is looking very complicated. You can note this down. Okay. But when you solve the problems, you will understand it better. Note this thing down, but I will do it in a different way. It's the same thing. Okay. Uh, the approach is the same, but the numbers might differ. So don't get confused. Okay. So I think we should take up a problem instead of noting down these formulas. Then it will make sense. Can we go ahead by skipping this? Don't note this thing down. These slides will be given to you. When I solve a problem, it will make more sense to you. Okay, don't note this formulas now. We will take up a problem immediately. Okay. Now, what happens is, uh, you have noticed that there was a beam, right? You had the major beam. Okay. Now, around the major beam, you are going to see some other beams coming in. They are called the grating lobes. Okay. Now, this happens in arrays, not in single antenna, because you have individual antennas coming together. Okay. Sometimes because the feeding technique is gone a little wrong, okay, you start seeing a lot of other lobes. They are called grating lobes. You don't want them, but they come around over there. Then there are techniques to actually get rid of them. Okay. So you actually cannot feed them uniform amplitude. When you feed them uniform amplitude, this is the problem that you face. Okay. So a lot of techniques are there to get rid of grating lobes. This is just for your information. Okay. Now, so you saw that one way is to reduce the separation less than lambda. If you increase the distance between the elements, then you start seeing grating lobes. See, the intention of having an antenna array is to have a focused beam. Grating lobes are taking the energy and putting it at some other direction. So, the technique that is important is, of course, the feeding. Feeding techniques are little complicated to handle given the scope of your syllabus. The one thing that you can understand is that the grating lobes can be controlled just by designing your array with distances less than lambda. All right, for you this much is sufficient. One technique to reduce grating lobes is to separate them with distances less than lambda. Okay. Now I want you to just revise this concept. We had taken two isotropic sources. We had given them a separation of lambda by 2, and we had given them the separation of lambda by 2. And when you feed the elements with the same phase, what do you get is the broadside array. So even if I take n elements, I will get broadside. What do you mean by broadside? The beam is perpendicular to the plane containing the array. Are you understanding? The beam will be perpendicular to the plane containing the array. When does that happen? When you feed the elements in the same phase and same amplitude, and of course that the separation is less than lambda. Okay, that we have understood. That is broadside. Now, let us skip this. We will not do this. We will straight away go to the problems. All right. So what I will do is I will go on. Jordan has lost his co-host position. I'm giving you back. I need the whiteboard. I will solve a problem now. Uh, okay. I hope all those online can see the screen. Those in the classroom have to ensure that you are able to see. Okay. So let us take a problem where we are to evaluate the half power beam width, first null beam width, and plot the radiation pattern for a 4-element array of isotropic sources excited equal amplitude and in phase. Okay. Somebody unmuted. क्या हो गया? हाँ? Hey, Parth, you will have to log out. तो मेरा आवाज कैसे आएगा? तू नहीं है लॉकडाउन? तूने ऐसा कितना ये किया है क्या कुछ सेटिंग? That is how you used to attend lectures, I think. किधर है पार्थ? No, you are not there here, Parth, in the list. Okay. Everybody has noted down the question. So we will start solving. Okay. Whenever we are solving such a problem of array where there are isotropic sources, what we get is the array factor. Okay. So now we do not have to derive. Remember when it was 2-element, we were deriving. We already have now the normalized electric field for n-element array. That is 1 upon n sine n psi by 2 upon sine of psi by 2. Is everybody okay with this? We already know this, okay? Now, what is n here, Parth? In this case, what is n? Huh? What is n, Parth? Very good. So n is 4. Okay. And what is psi? What is psi? Kd cos phi plus delta. Very good. Okay. So we have this with us. Kd cos phi plus delta. What is k equal to? 2 pi by lambda. And what is d in the problem? What is the distance d in the problem? I had given it, no? I did not write in the question though, but I mentioned it, right? So the d over here is lambda by 2. Okay, I had mentioned it, forgot to write it down. Okay, so your d is lambda by 2. So cos phi, what should be delta? If it is in phase, 0. Very good. So this is the thing. So if you tell me what will be psi after you evaluate, you will get pi cos phi. Right? Okay. Now I'll go to the next slide. You have copied it down. So
Ma'am,
now,
1 second.
yeah, okay. Those of you who are waiting can go and write down the E normalized to be 1 upon 4 sine 4 into pi cos phi upon sine pi cos phi. You're getting what I'm saying? Write it if you have understood.
Yes, ma'am, done.
Check. Okay, so I'm writing now En is equal to sine 4. What was psi? Pi cos phi upon 2, correct? Upon n, 1 by n. Now sine pi cos pi by 2. Is everybody okay with me writing like this? Then I will do the adjustments. I will get sine 2 pi cos phi upon 4 sine pi by 2 cos phi. I hope it is visible. Yeah. Okay. Now let us analyze. This is a fraction. Okay. The electric field now is a fraction which is having a numerator and a denominator. Now, whenever you want a fraction to strike the maximum, the best thing is to get the denominator to 0. Do you agree or not? When the denominator becomes 0, then we have the fraction going to maximum. Now, look at the denominator. The denominator will become 0 and it will become 0. It's a sine function only when the angle of the sine function becomes 0 and pi. Okay. So that's why I didn't want you all to write the formulas there. We will solve it with the problems itself. So you have the main lobe or the major lobe coming in only when this angle pi by 2 cos phi. It's very specific to the problem now. We are only talking of main lobes to this problem. Don't apply it to any other problem. Okay. We get the En for the particular problem. Now, in that problem, the fraction, we look at the denominator. So, pi by 2 cos phi should become 0 or it should be pi or whatever. It should go to m pi. I hope you are understanding this and you have the calculators with you. I do not want you all to use your phones because then you do not get enough practice. You end up struggling in the exam. So please, those who are at home also, please take your calculators and start calculating. Okay, now let us take the first case wherein we say that pi by 2 cos phi, okay, is equal to 0. Okay. Now, when it is 0, that means my cos phi is 0. That means my phi should be pi by 2 radians or 90 degrees. That means your major lobe is situated at 90 degrees. But if I say minus 90, will that be okay? minus 90. So if I see cos of 90 is 1, cos of minus 90 is also 1, because cos is immune to the minus sign. Okay, that means I can say that my major lobe resides also at minus pi by 2. So everybody is comfortable with this. We should not leave the problem like this. Let's go ahead and put a pi, okay, and see what happens. So now I will take a pi by 2 cos phi, because all of us have agreed to understand that we are having the denominator 0 at two locations. One is 0 and pi. Of course, 3 pi, 4 pi, 2 pi also. Okay. So let us see what happens at pi. Okay, sorry. You will have a 2 coming here. So cos phi will become 2. Now phi becomes cos inverse of 2. This is not possible. So even if you now take 2 pi, 3 pi, 4 pi, it is of no use. Okay. So now we have declared that our major lobes are at only 90 and minus 90. Okay. Now going ahead with the next. Let us evaluate where are the nulls. Okay. Now let's go back to our En. Okay. When will you get your electric field to 0 in a fraction? When the numerator becomes 0. Okay. Now, when will the numerator become 0? When sine of 2 pi cos phi becomes 0. That means the angle 2 pi cos phi should be 0 or pi. Okay. What one? Angle. Okay. So tell me, where will you get the nulls? When you have 2 pi cos phi is equal to what? 0 degrees, or it will be pi and so on till m pi. Everybody agrees? Let's start now. Let us put the first fellow. Let us put 2 pi cos phi equal to 0. So then cos phi is equal to 0. Now phi is equal to 90. This is conflict of interest. Just now we said that our maxima is coming. See, the denominator rules. It's undefined. That means over here you cannot have a null. What resides at 90 is major lobe. So this state we will say so we were not supposed to take this. But anyway, you have to keep calm and understand this. You have to solve problems. Next is 2, because it's a fraction. In a fraction, the denominator, overrides everything. The denominator has become 0. So there is a major lobe there. All right. Now the next state is 2 pi cos phi equal to pi. Then what happens here? Cos phi becomes half. So phi becomes what? Pi by 3. They are younger. So I leave that to them. They remember faster than me. They are younger than you. They are right. Pi by 3. Okay. Pi by 3. Can we also have at minus pi by 3? Yes. Okay. And minus pi by 3. What is pi by 3? 60 degrees or 30 degrees? Okay. So please remember this, 60 degrees and minus 60 degrees, you have the nulls. Okay. Now, if you put anything else, let us check. We must not leave it like that. Okay. What we will do now? A 2 pi also was possible, no? We have taken pi. A 2 pi also is possible. Everybody agrees? So let us take that 2 pi cos phi equal to 2 pi. Cos phi is equal to 1. That means your phi should be, huh? Phi is what? 0.
0.
Did we get anything at 0 degrees so far? Did we get a null there? No. Apna previous null was at 60 degrees and minus 60. Our major lobes were at 90 and minus 90. And our another null has come at 0. Can I have it at pi opposite? Because this is a symmetrical pattern. 0, if you see on the chart, 0 ke opposite, you have pi. Keep this information in hand. It will be important. They go hand in hand. At 180, there was nothing so far. Nothing you have evaluated so far. Otherwise, you'll get half pattern. आधा मिलेगा आपको. Okay? If you only go with 60, you will not get, because minus pi is also there, no? When 2 pi cos phi is equal to 2 pi, there is minus 2 pi also. So cos phi becomes minus 1. Then phi becomes 180. Are you understanding? Do it this way or keep doing everything. What is better? Once you get one, evaluate its opposite mein kya hai. I hope everybody is understanding this. Okay, because there is a minus 2 pi also. Okay, so we got nulls. If you take 3 pi, will you be able to handle it? Yes? What? You will not get any angle only. Cos function is only between plus 1 and minus 1. So if you put a 3 pi minus 3 pi now, you will end up getting nothing. Phi will not exist. Agreed? Okay, so this much nulls is all that we have. So now let's go ahead with the half power points. Okay, now for half power points, those online, are you all able to understand? Can I have a feedback from you guys?
Yes, ma'am.
Jordan, everything is okay so far, understood? It's a very
Yes, ma'am.
important question. You need to do this well. Okay, now let's understand for half power points. Now I invite you guys to look at this expression of electric field. Okay, now what you need to understand is, you will have to take this from me, that for half power, okay, because this derivation is very difficult for you, your 2 pi cos phi, okay, 2 pi cos phi should be equal to plus minus 1.391 radians. This is where you will have your half power points. You will have to remember this. 1.391. This is where you will have your half power point. That's the angle in the numerator for the sine function, takes on a value of plus minus 1.391. All right. Now, let us evaluate cos phi, okay, when it is 1.391 divided by 2 pi. So, plus minus 2 pi. So, what is your phi going to be? Huh? I know you are giving me in radians, but unfortunately my answers are in degrees, because I wanted to plot. How much radians are you getting? You don't have a calculator? One point.
0.221.
I'm getting a different answer here. How much?
0.22.
Sorry?
0.221.
Is this what we are getting?
77.2 degrees.
Is that all that you are getting? Is there another angle as well? 1.34. Pratham,
Yes, ma'am.
how much are you getting?
I got cos phi as 0.221.
Cos phi is 0.221. What is phi, Pratham? Okay, what is
Cos,
phi?
cos inverse of 0.221, so I got 1.34 radian.
Pratham, 1 minute, huh?
When I do cos,
1.34.
yeah, 1.34 radian.
So I was asking for phi, no?
Oh.
So 77.2 degrees, okay? And what about the other angle? It cannot be 1. So 102.76 degrees. And radians, how much? Whatever it is, okay? You have to note down. All right? Okay, now after this, everybody okay so far? Minor lobes. Minor lobes will be at, you have to remember for half power points, we said the angle in the numerator was plus minus 1.391. Now, for minor lobes, there are other lobes other than the major lobe, chote lobes. Okay, those lobes will be at plus minus 2m plus 1 pi by 2. This you have to remember. So, and what is going to be m? M will be not 0. It will be from 1, 2, 3 onwards. Okay, so then cos phi will be equal to plus minus 2m plus 1 upon 4 here. Now, when you take m equal to 1, okay, you will get phi equal to 41.40 degrees. Then another one you will get at 138.5 degrees. Please check. You will get two angles. When you place, okay, I will move ahead. Everybody understood this? Now, in the next 5 minutes, let me finish this topic. So now I am drawing the pattern. This is 0 degrees. This is 90. This is 180. This is 270. Okay. Now you have to tell me where was the half power point. Where was the major lobe? At 90. Okay. Major lobes were at 90 and minus 90. Correct? Where was the null? 60 degrees. Okay, so I will say there was a null here at 60 and there was a null here at minus 60. 0 and 180 also there was a null here and there was a null here. Okay. Then where were the half power points? 77. Okay. So at 77, something like this, half power. And which is the other one? So something here over here, half power point. Barabar? So half power I will mark here something like this. Anything else? Minor lobes. Where were the minor lobes? 41 degrees. Okay. 41 degrees there were minor lobes. And which is the other one? 138. Somewhere here.
135.
Okay. Now see. There is a major lobe here. Now how I'm going to draw the pattern? There is a major lobe here. It drops to half power here. Everybody agrees so far whatever I have drawn? Now you see there is a null, so I have to bring it down here. Right? After that, there is a null over here at 180 and 80, but there is a minor lobe here. It has to go down. Then again on this side. And do not forget to repeat the same thing at the bottom because you have not taken all integers. Remember. Okay. So you will have to draw a symmetrical pattern over here as well. So this is your pattern. Now what is going to be a half power beam width then? See, half power beam width has to be like this between the half power points. Where were your half power points? 90 minus 60 degrees. No, sorry, what was that? No, one side was 102, the other side 77.2, na? 77.2, something like that. But you have to take 2 times. It is equal. Check karo. Aega. So how much is your half power beam width? Huh? 26. Multiply by 2. Huh? 25.2, 26. Somebody saying, okay, fine, 26 degrees. What will be first null beam width now? First time the lobe goes down to null is at 60 from 90. So 30 degrees on one side. Because your major lobe is at 90 minus 60 and 2 times either side. This is your first null beam width. So how much is that? 60 degrees. Huh?
60.
Okay. And now for directivity, for directivity, in the case of broadside, please remember, for broadside, this is the broadside array because we have fed them equal amplitude and equal phase. Equal phase we have fed. So directivity of such an array is 2 times the number of elements spacing divided by lambda. So what was it? 2 times multiplied by 4 multiplied by lambda by 2 upon lambda. So directivity comes to be 4. Is that clear? Now I want you all to practice the other question. 4 element array. Same question, only that you have to feed them opposite in phase. You have to feed them opposite in phase. I will put up the solution. But the directivity of antenna array which is fed, okay, I will just tell you the question. Can I go to the next slide? So the question that you need to practice, it is on same grounds, same method. 4 element isotropic sources you have to take. Fed equal amplitude opposite phase. And you have to find out the HPBW, FNBW and directivity as well. The directivity will be different because this is opposite phase. Of course, you take D equal to lambda by 2. Okay. The Directivity for an end fire. This is called an end fire because you're feeding it opposite in phase. The directivity will be different. It will be 4 times ND by lambda. Okay, 4 times ND by lambda. All right. This I will give you the solution, but for your exam, please change the number of elements to 5 and 6 and practice. Give it equal amplitude, equal phase, equal amplitude, opposite phase, and practice this. Are you understanding? All right. With this, I will stop the class. I will call you all tomorrow also online. All right. Any doubts? Can I stop sharing the screen? I want to take attendance. Wait.
Yes, madam.
मुझे पता ना, अगर तुमको दिख रहा है वहां पे तो ऋषि नहीं है, हृदय नहीं है, आयुष नहीं है, अभिनव है, हर्ष नहीं है, स्वानंदी है, वो थी ना, स्वानंदी, मिसबा, यशस, मयूरेश नहीं है ना? नहीं, अगर है तो बोलो। क्रिस्टोवल, सार्थ, प्रथम, स्वरा, सपना, नो ना? यस है तो बोलो, डोंट से ये नो, ऐसा मत बोला, गेट कंफ्यूज। सपना नहीं है, ऋषिकेश, नेहा, मुशाम, कुणाल, वैभव, कानडे, तन्वी, प्रिया, शाहरुख, यश, नंदना, रोहित, पुष्कर, प्राची, मयंक, सूरज, सक्षम, नमनदीप, खुशी, अमित, हर्षित, पार्थ, जॉर्डन, आर्या राशिनकर, दर्शन, सार्थ, ओसीना, तन्वी, तीर्थ, अतिया was there ना? तीर्थ, तीर्थ एब्सेंट है। यश शिंदे, श्रेयस, देवांश, विघ्नेश, विघ्नेश था ना? गया ना? नहीं है ना अभी? विनीत, रजा, आर्या तालेगांवकर,
Yes, ma'am.
साक्षी, तालेगांवकर एब्सेंट, साक्षी, अश्लेषा, अश्लेषा है,
Yes, ma'am.
सुजल, सुजल तांबे, अनुष्का तेवर, काव्या ठक्कर, विभव त्रिपाठी, अमान, कौस्तुभ, वंश, आर्या, जादव, युसरा, दर्शन,
Present, ma'am.
तो दोनों दर्शन थे, केनेथ, सुजल, दिशा, स्नेहा सवेकर। चलो जाओ क्लास में, तुम्हारे
Ma'am.
VLS है ना क्लास, भागो भागो। I have taken the attendance. You all can leave. Arya Talegaonkar is present. Oh, sorry.
Yes, yes, ma'am.
Okay, okay. I'll do that.
Yeah.
Please leave the meeting.